All right, our last lesson for Chapter 8, we're going to focus on something called the rational root theorem. So let's look at this definition and then we'll talk about it and do some examples. The rational root theorem says possible rational roots of any polynomial are combinations of p divided by q, where p represents all positive and negative factors of the constant. Remember, the constant is the term on the end without your variable in a polynomial, and q represents all the positive and negative factors of the leading coefficient. So if you take all the factors of p over all the factors of q, that will give you possible rational roots of the polynomial. Just a reminder, rational numbers, a decimal representation of a number that either terminates or repeats. So we are trying to find rational roots for polynomials. Just real quickly, if we take a look at x squared plus 5x plus 6, and we know that this would factor down into x plus 2 and x plus 3. So x plus 2 is a factor, x plus 3 is a factor. The roots would be negative 2 and negative 3. Remember, if you were to set each of these equal to 0, you would get that negative 2 and the negative 3. So that's what we're working on, but our examples aren't always going to be that straightforward where it's something you can just factor to get your two roots right away. And so how do you go about getting your rational roots? Well, that's where the rational root theorem gives us a kind of a guide to follow to get where we need to go. All right, so use the rational zeros theorem or rational roots theorem, same idea. A zero is the same thing as a root, to find any rational roots. If it has at least one, solve it completely. So what we want to notice with our example is we have everything on one side and 0 on the other side, so that's set up. Our leading coefficient is 1, that's going to be your q, and your constant term on the end is negative 6, that's going to be your p. So basically what we're looking at are factors of p over factors of q. Or we can actually put those numbers in. Factors of 6. Now I just noticed this is a negative 6. I don't know what you guys have typed in your notes. Let's make that a positive 6 because that's what the example should be. So if you have that as a negative 6, let's go ahead and change that. So we're going to look at factors of 6 divided by factors of 1. All right, so the thing with all of our factors is you can have positive and negative factors. So I'm just going to put the positive and negative out front. We know that's going to apply to all of our factors. So then let's lift out the factors of 6. Well, your factors of 6 are 1, 2, 3, and 6. And you can see those factor pairs. 1 times 6 is 6, 2 times 3 is 6. And then factors of your q, which is 1, is just a 1. So now what we're going to do is we're going to divide those out and say, okay, so our possible roots could be 1 divided by 1, which is 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1. So these are all possible rational roots. We don't know if they're going to work or not, so we're going to test those one at a time. When we get one that works, then we can break this down and solve, hopefully with factoring a little bit easier. So if we go back to our original problem, we have x cubed minus 7x plus 6. So let's start with our 1, and let's do synthetic division. So synthetic division with that 1, we want to see if 1 is a factor of our polynomial, or if 1 would be a root. So I kind of wrote all over up there. I'm going to rewrite it. It's x cubed minus 7x plus 6. So we write out the coefficients. We have a 1 for the x cubed, we have a 0 for our x squared, we have a 7 for our x, and we have a 6 for our constant. And I don't know if you guys noticed that 7 actually is a negative 7x, so we do need a negative 7 right there. Alright, so then we do our synthetic division that we did in our last lesson. You start by just adding down your first number, then you multiply. 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, -7 plus 1 is -6, -6 times 1 is -6, and when you add that you get a 0. Now if you get a 0 here, that means that it worked. That means that that 1 is a rational root. So because we found a root that worked out, and again, if this 1 hadn't worked, we would go on and we would try 2, 3, 6. It might seem like a lot of work, but again, the synthetic division is pretty fast, and we just want to find a root that works out. Now what we do is we take a look at what our answer would be. So again, that 0, that means that we did not have a remainder, so that 1, we were able to divide by that 1 very easily. So here is our constant, here's our x squared. So now we're going to have x squared plus x minus 6. And then is this something that we can factor? Because now that it's an x squared and it's a trinomial, this is easier for us to do. The original problem had that x cubed, and that's why we started with the rational roots theorem. Are there factors of -6 that add up to? Are there factors of this -6 that add up to this one? Well, you might say, yeah, +3 and a -2. Oops, there's my x. And then you set each one equal to 0, so you get a -3 and a +2. Those are our roots. And remember, we got that 1 to work out in the beginning, so 1 is also a root. So these are all the roots of our polynomial. Alright, so for this Name That Tune, this is a concert I went to in college. It's actually not the group for the song I'm going to play, but one of the founding members of this group, after the lead singer died in the 90s, then some of the members kind of split apart and formed their own pieces of whatever they were doing. And so the bass guitarist, Phil Lesh, formed a group called Phil Lesh and Friends, and they came to Miami, where I went to school with Bob Dylan. And so this is a song from his band before the lead singer died, and they ended up breaking apart.
Sugar magnolia, blossoms blooming, heads all empty and I don't care. So my baby down by the river, who should have to come up soon for air. Sweet blossom, come on, under the willow, we can have high times if you look back. We can discover the wonders of nature, rolling in the rushes down by the riverside. She's got everything we like for, she's got everything.